Hey everyone, let's just jump right into today's explainer. You know that static, brightly colored poster hanging in literally every science classroom you've ever been in? Well, today we're taking that poster and transforming it into what it truly is. We're going to decode the periodic table, and let me tell you, it is the ultimate thrilling blueprint of the universe.
To really set the stage for us, Nobel laureate Glenn T. Seaborg completely hit the nail on the head. He pointed out that the chemical elements, they aren't just some random cluster thrown together by chance. They display these amazing trends, and they actually live together in families. So if we want to disentangle the world and see how everything is built, we absolutely have to understand this table.
But, getting to this beautiful level of organization, not easy at all. Just imagine the absolute chemical chaos those early scientists were facing. Back in the year 1800, we only knew of 31 elements. 31, that was the whole puzzle. But then, by 1865, that number had doubled. And today, we're looking at over 114 known elements. Modern scientists are literally synthesizing brand new ones in labs. Figuring out how all these pieces fit together was just a monumental puzzle that desperately needed sorting.
So here's our roadmap for this explainer. 1. Taming chemical chaos. 2. Mendeleev's missing pieces. 3. The modern blueprint. 4. The element neighborhoods. And finally, 5. Reading periodic trends.
All right, part 1. Taming chemical chaos. Let's look at early classification.
Those early scientific detectives started noticing these tantalizing patterns hidden right within all that elemental madness. The 19th century saw this rapid-fire succession of classification attempts. Like in 1829, Johann Dobereiner noticed similarities in groups of 3 elements. He called them triads. Then, in 1862, de Chancertois actually mapped elements onto a cylinder. And by 1865, John Alexander Newlands proposed what he called the law of octaves. He beautifully, though, a bit imperfectly, compared the recurrence of chemical properties every 8th element to musical notes on a scale. Honestly, it's like a giant puzzle. And all of this laid the groundwork for a massive breakthrough in 1869 by Dmitri Mendeleev and Lothar Meyer.
Moving right along to part 2, Mendeleev's missing pieces. Now, the true genius of Mendeleev, it wasn't just in how he organized what was already known. Nope, it was in what he deliberately left blank. Take a look at his 1905 table. He organized the elements by increasing atomic weight, right? But when an element didn't quite fit a column's chemical properties, he just actively ignored the strict order. He assumed the measurements were flat out wrong, and he left these deliberate, gaping holes for completely undiscovered elements, like one he temporarily named Eka aluminum. And this right here? This brilliantly illustrates the jaw-dropping predictive power of science. Just compare Mendeleev's predictions for that Eka aluminium to the actual element, gallium, which was discovered years later. He predicted an atomic weight of 68. It was actually 70. He predicted a density of 5.9. It was 5.94. He basically described gallium down to its chemical formula before anyone on Earth had ever laid eyes on it. I mean, no way, right? That is absolutely wild.
Which brings us to part 3, the modern blueprint.
So, as our narrative shifts into the 20th century, the puzzle kind of pivots. It moves away from atomic weight and aligns with the deep internal rules of quantum mechanics. In 1913, an English physicist named Henry Moseley conducted these X-ray experiments that proved, actually scratch that, it completely revolutionized our understanding. He proved it isn't atomic mass that drives the elements, it's the atomic number, meaning the number of protons in the nucleus. This single discovery modified Mendeleev's work into the modern periodic law, which states that chemical properties are periodic functions of their atomic numbers. And that, my friends, gave us the IUPAC standard long-form table we use today with its 18 distinct vertical groups.
Oh, and there's also a really fun linguistic puzzle that comes with this whole modern blueprint. When scientists started synthesizing these highly unstable, super heavy elements, the ones with atomic numbers over 100, they actually started fighting over who got to name them. Seriously. So to avoid these crazy laboratory naming wars, IUPAC created a super strict system. You just break the number into Latin and Greek roots. Let's take an undiscovered element like 120. 1 is un, 2 is b, and 0 is nil. You stitch them all together, add em at the end, and boom, you get un, b, nil, em. How cool is that?
All right, part 4, the element neighborhoods, the S, P, D, and F blocks.
Where an element lives on the table tells you pretty much everything you need to know about its personality. Think of it as this perfectly well-planned city divided into 4 main blocks: S, P, D, and F. And the specific neighborhood an element belongs to? That's dictated entirely by where its very last electron gets added. The S block is home to those highly reactive metals. Then the P block contains our nonmetals and stable gases. The D block, right in the center, that houses the transition metals you probably know really well, like iron and gold. And finally, that F block, down at the very bottom, holds the inner transition elements, which includes the big radioactive heavyweights. To really see the stark contrast in these neighborhoods, let's compare the extreme left to the extreme right. Over on the left, the S block metals have just 1 or 2 outer electrons, and they are completely desperate to get rid of them, which makes them just wildly reactive. But travel all the way over to the far right of the P block and you hit the noble gases. Their outer electron shells are perfectly full. They're completely stable. Sitting right next to them, though, are the halogens, and they are incredibly greedy. They just want to grab one more electron to reach that perfect, stable state.
And that brings us to our final section, Part 5, Reading Periodic Trends.
Okay, so now that we know the neighborhoods, let's learn how to actually read this map. And we'll do it with a really counterintuitive riddle. Think about this. As you move from left to right across a single row, or period, you are adding more protons and more electrons. You are literally adding more stuff. And yet the overall size of the atom, its atomic radius, actually gets smaller. So why on earth does adding more pieces make the atom shrink?
Well, the absolutely crucial point here is a concept called effective nuclear charge. Just think of the nucleus like a giant magnet. As you move across a period, you're adding electrons into the exact same outer shell, but you're also adding protons to the center. So that positively charged nucleus just gets stronger and stronger, and it pulls those outer electrons closer and tighter. The magnet gets stronger, literally shrinking the atom as you move from left to right. It's fascinating. But wait, look at what happens when you move vertically down a group. The whole trend completely flips. Moving down a column adds entirely new energy shells, layer upon layer, kind of like an onion. And these inner layers literally shield the outermost electrons from the magnetic pole of the nucleus. Because of this massive shielding effect, the atom just swells dramatically in size. Plus, those loosely held outer electrons make the element act way more metallic.
So by simply reading these trends, like size, reactivity, metallic nature, you can look at any element's location and almost instantly deduce its behavior. We've gone from this chaotic list of 31 substances to a perfectly ordered, beautifully precise quantum map, which leaves us with one incredibly exciting question, right? If this table so beautifully predicted the foundations of our known universe, what unimaginable, totally bizarre new elements might we synthesize in the future as we push far beyond element 118? Those blank spaces are still waiting. Thanks so much for joining me on this explainer, and hey, keep questioning the universe.